Hey guys, welcome to Bonding Lesson 3. This is a little bit longer one. It'll take about 15 minutes, but take a look at your goals. I want you to understand covalent bonds are between non-metals. Very important. I'm certain that that will show up on a quiz. Understand the relationship between bond length and bond energy. And then understand the octet rule and its connection to energy. Alright, let's get going. Many chemical compounds, including most of those found in living things, are composed of molecules which are neutral groups of atoms held together by covalent bonds. So neutral, let me change my pen color here. And by the way, my dog is very antsy. Everyone's ready to do something other than sit still today, so sorry if you can hear them walking around in the background. Alright, molecules, neutral groups of atoms held together by covalent bonds. Atoms held together. Let's just put covalently, but of course that is covalent bonds. Okay, a molecule's chemical formula are the atomic symbols and subscripts that show the relative numbers of atoms of each kind. For example, you have H2O. One water molecule contains one oxygen joined by separate covalent bonds to two hydrogens. All right, and our other example here, example 2, we have O2 is two oxygens covalently joined. This is a diatomic molecule that contains only two atoms that are the same. Homonuclear diatomic molecules, H2, are different. Heteronuclear diatomic molecules have a different molecule in two of them. But a lot of molecules, especially the gases, the nonmetals, will be found as diatomic molecules in nature because that's where they have the lowest potential energy. Remember that. I'm going to be coming back to that over and over and over again. Your third example of a molecule chemical formula is one that I have written on a lot of our things in the lab, and that is for sucrose. C12H22O11. That means it has 12 carbon, 22 hydrogen, and 11 oxygen that are covalently bonded. Notice all of these atoms involved in the covalent bonding that make up these molecules are nonmetals. Oops, sorry, didn't have my pen on. They are nonmetals. That's going to be on your quiz, so make sure you understand that. And remember, looking at the periodic table, you've got your metals here, your transitions here, your nonmetals are over here. Okay, on the right. Non-metal. Okay, don't forget. So oxygen and carbon, we're back up here now, can each form more than one bond. Carbon can form 4, if you'll remember the disturbing video we watched. They can form 4, and then oxygen can form 2. This ability to bond multiple times allows very large molecules to form. That allows very large molecules to form, such as those that make up living things, proteins, carbohydrates, and lipids. So look at your picture here. Okay. In a stable covalent bond, the attraction between the positive nucleus, right here, and the negative electron cloud, right here, is balanced with the nucleus and electron cloud repulsion. When this energy state occurs, covalent bonding is complete, and electrons from all atoms involved are now shared, and a stable molecule is formed. And here, the arrow indicates, I'm down here. In figure 6, the arrow indicates the attractive and repulsive forces between the electrons and the nuclei of two hydrogen atoms. Remember, electrons are negative, and you've got two atoms, okay, and the nucleus has the positive protons, even though they are attracted to one another and end up bonding covalently, these repulse one another just as these repulse one another. So in order for things to bond, there has to be a benefit to them coming together, even though they are repulsed. And we'll talk about that in this picture down here below. So if you look at this next picture, figure 5, okay, this is where it all comes together, why they're able to overcome those repulsive forces. And I meant to circle it, I've kind of marked through it. It's potential energy. It's all about the potential energy. This is the distance between the hydrogen nuclei, which are both positive, correct? And then this is the potential energy over here. You'll notice when they're at this distance from one another, potential energy is very high. They're not going to bond when they are that distance to one another, nor are they going to bond over here when they're that far apart. Even here, you'll notice. But there's almost a magical thing that happens when they're at this distance, 75. I'm not sure what the PM stands for. Picometers. It would stand for picometers. That makes sense. Okay, so when they're 75 picometers from one another, they're positively charged nuclei, that's the perfect place to be. And at that place, their potential energy drops substantially, and that's when bonding occurs. So let's get some language down for that. Okay, it says, notice in figure 5 that a stable molecule of hydrogen occurs when two hydrogen atoms are 75 picometers from each other, nucleus to nucleus. This is known as the bond length, which is the distance between two bonded atoms that achieves the minimum, I'm going to go down here, the minimum potential energy. That achieves the minimum potential energy. If you remember on page 1, we had the big lightning rod that I wanted you to remember in this whole unit. It is all about energy. That's why things bond. When they're at the perfect potential energy, that's when bonding happens. Just like right here. Okay? Otherwise, the potential energy is too high and they will not bond. And so we're back here. And it says, so the bond length of the hydrogen-hydrogen bond is in H2 is 75 picometers. In order to break a covalent bond, you have to put that much energy back into it to overcome it and break that bond. And that's on the next page or the bottom part of yours. So the same amount of energy that was released in the formation of the bond must be added. And this is the bond energy. It's the energy required to break a chemical bond, and form neutral isolated atoms, Okay. It's a general rule. As bond length shortens, bond energy increases. So the shorter the bond, the more bond energy. And again, bonding occurs naturally as elements seek a noble gas configuration. Remember, this is when they have the lowest potential energy. They're the most stable. Everyone wants to be a noble gas. Okay. The noble gas configuration is when covalently bonded atoms sharing electrons in overlapping orbitals. That's how they're sharing. They're sharing by overlapping their orbitals in the valence or outer electron shells. Allows each of the atoms to experience the effects of the stable noble gas. So take a quick look at your orbital diagrams in your notes here. These are just to show visually the overlapping orbitals, where they would occur, and how to achieve the octet rule. If you will follow my cursor, the first one's pretty easy. We've got a hydrogen that has one valence electron with another hydrogen that has one, because they both have one, and their goal, remember, hydrogen and helium only want two. They can't have 8. So it's going to look for another hydrogen. They're going to share this orbital. It's going to have 2, and it's going to feel like a noble gas. Okay, down here we get into the larger molecules. Now don't forget, even though this is 1s, we don't have to worry about that. It's not in the valence shell. It's not in that outer electron shell. We're just looking for the highest energy level, which is 2. And in 2s and in 2p, we have 2, 4, 6, 7 total, which we know fluorine is in the 17th group, so it has 7 total, but this is just drawing it out for you. We've got another fluorine that has 7 total, so they are going to covalently bond and share so that they can have that noble gas configuration. Now when this one borrows this one, it has 8, and when this one borrows this one, it has 8. Same thing down here when they're not the same. Hydrogen has 1. It can have up to 2. It would like to have another one. Chlorine, remember, we want to go to the highest energy level. 1 is not it. 2 is not it. Looks like 3 is it. So we've got 2, 4, 6, 7 in that highest energy level. It wants one more. Hydrogen would like to have one more as well. So it's going to work out perfectly because hydrogen gets to share this one right here, and chlorine gets to share the one hydrogen. They both end up with their noble gas configuration. That's what covalent bonding is all about. Okay, the last thing we want to touch on today is the octet rule. It is the octet rule. I'm going to put this like this because we're going to talk about how it's not always a rule in just 1 second. Well, more than one, but a few seconds. So the octet rule is when chemical compounds tend to form so that each atom, by gaining, losing, or sharing is what we've just been studying in the covalent bonding, has an octet of electrons in its highest occupied energy level. Okay, just for your vocabulary, recall that that is your valence shell, or your valence electrons. You need to make sure you know that well. The octet rule, there we go, I've put it in quotes there, states compounds tend to form, meaning the rule generally predicts how compounds will form, but there are exceptions. There are always exceptions. I've not found hardly any rule in chemistry where there aren't at least a few exceptions. You will need to be familiar with these because they're very important, especially if you move on into the higher levels of your chemistry education. Okay, so the first one is the hydrogen-helium exception. That one is pretty self-explanatory, and I bet you could figure it out on your own, but that's because they only have 2 total electrons even possible. All right, they're only going to at maximum have 2 valence electrons, so they are not going to subscribe or follow the octet rule for 8. It's just not going to be possible. Now the next one I would not expect you to know, but you do need to memorize this one. It is boron. Boron tends to form bonds that achieve a valence electron configuration of 6. 6 valence electrons as opposed to 8. For example, boron trifluoride. And then the third one is going to be the expanded valence. Expanded valence. And again, that's pretty much what it sounds like. It's when elements can be surrounded by more than 8 electrons when combined with highly highly electronegative elements, fluorine, oxygen, and chlorine. Bonding occurs not only in the s and p orbitals, but also in the d orbital. And some examples are PF5 and SF6. That would be phosphorus pentafluoride and sulfur hexafluoride. I will let you explore these exceptions as we learn about Lewis dot structures, and I think it will make more sense then. But just remember, even with the exceptions, they are going to want to do what they're doing because they have the lowest potential energy in those particular configurations. Have a great rest of the day, and don't forget to look back at your goals so you'll be ready for our quiz.